Okay, in this exercise here, you're going to see the integral test for convergence of serious or non-negative terms in action. And you will see why it's useful. In particular, if you see these two integrals here, you will see, these two series here, you will realize that trying to assess the convergence of these is complicated, in particular because you have to apply something like the Cauchy's convergent test, and that is a bit clumsy to apply that. And you will see that with this, with the integral test, this is going to simplify a lot. Let me remember you here what is the integral test. The integral test says that if you have a function which is decreasing, right, monotonically decreasing, and it's not negative, right, then this series and this integral both converge or divert simultaneously. Okay, so that means that we can assess the convergence of one of the series using the integral, or the other way around. And actually that's what we have to do in these cases. In these two cases we have to assess the convergence of this series using the integral, and in the other case we have to do it the other way around. Okay, so let's see. Let's focus on the first integral here, the first series here, right? So what we have is this, and so we can just calculate the integral. Doesn't matter the lower limit. You can put any lower limit that you prefer. So let's say 2, that's okay. From 2 to infinity of dx over log x to the power log x. The nice thing about using the integral is that you can make a change of variable, and the change of variable here suggests itself, right? So the change of variable is log x is equal to t. This is what is complicated here, right? Okay, so once we have this, then of course x is equal to et, right? And dx is the exponential of t dt. We can substitute back here. We have, well, the integral from t is going to be the logarithm of 2 in the denominator, and infinity here. As I said, the lower limit doesn't matter much, right? And then we have dx, right, which is the exponential dt, and down here we have t to the power t dt. Okay, now we have to decide whether this integral here is convergent or not. And you may think that the problem is still complicated, because trying to find a primitive of this is complicated, and or deciding whether this integral is easy to this integral is convergent or not is not easy to handle, right? However, we can apply again the integral test and say, okay, this integrand here is a function that decreases. How do I know that it decreases? Because the exponential is, the limit of this function is 0, because this one goes faster to infinity than this one here. So this is going to 0. So actually it's decreasing. This function is positive and decreasing. So what we can do is to, instead of deciding whether this integral is convergent or not, we're going to see what happens with this series here. And you might be thinking that I started off from a series, then I go to an integral. I don't know what to do with the integral, and then I go to a series, but the series I started off from is this one, and the series I have to decide now is this other one, which is another story. Because actually for this one, it's very easy to decide what happens. All we have to do is to apply the root test. This is an, okay, it's a non-negative series, right, as you can see. So all we have to do is to calculate the nth root of an, and that is simply e over n. This limit is 0, therefore this series converges. And that is very easy to assess, as you can see. If this series converges, then this integral converges, and if this integral converges, which is equal to this one, then this series here converges, right? Okay, so here's one of the ways that you can apply this, right? Let's try to apply it to the second one. Okay, let's do the same thing here. So we're going to decide what happens with the second, and we're going to do the same thing. We start from the integral, right, and try to decide whether this integral converges or not. So we have logarithm of x to the power logarithm of x, logarithm, sorry, of logarithm of x. Okay, that is what you have here. So what we're going to do is we're going to use the same change of variable as we've used before. So what we're going to do is to obviously do this, right? Because the logarithm is what is getting complicated here. So again, what we have is x is equal to et, and dx is et dt. We substitute here, we have the logarithm of 2, and here we have infinity. Then we have, in the denominator, we have t to the logarithm of t. In the numerator, we have et dt. And just as we've done before, instead of deciding about this integral, which looks still complicated, we're going to decide about this other series, sum from 1 to infinity of, well, let me take 2 here. Doesn't matter the way you start, right? E to the n, and down here you have n to logarithm of n. Why? Because again, I can apply here the root test, okay? And if I apply the root test here, what I get is e here, and down here I have n to log n divided by n. Okay? So you have now in the denominator, so you have to decide the denominator is just a constant. So you have the denominator, right? And you have to decide whether this is, well, what is the limit of this, right? N goes to infinity. However, the exponent goes to 0. So actually you have here an indeterminacy, right? So let's see what to do with this. Log n over n. And what we're going to do is to calculate what is the logarithm of this, and that will be the logarithm of the limit. If we do this, what we have is the logarithm of n over n, that is the exponent times the logarithm of n. So we have the logarithm of n squared over n. However, this goes to 0 when n goes to infinity, right? So if the logarithm of this goes to 0, it's because this goes to 1, so the limit of this is e when n goes to infinity. And what happens if we have a function here whose limit is, in which the n root of the general term goes to a number which is larger than 1, is that this is divergent. Okay? So if this diverges, this integral diverges, and if this integral diverges, so does this series here. So this is a divergent series. And finally, in the last one, we have to do the opposite. Okay, we actually are starting here from an integral, and we have to see what happens with the convergence of this integral, and we're going to do that transforming it into a series, right? So the series we're going to deal with is this one, which we have already dealt with before. Actually, this is an, it's just the root test where you have to apply, sorry, this is an, and this is just e over n, which goes to 0, so this one is convergent, so this one converges. No surprise, because that's the integral that we have to obtain doing the change of variable in the integral test of this one. Okay, that's it.